So please, warm afternoon welcome for our friend Tim. Welcome, Mr. Weber.
Hello. So I'm actually really thankful for my timing here at about a little after 3 because no one wants to see me dance at all, and I'm not a big dancer, so I'm glad I missed that. The title of my talk is Imagine the Possibilities of 3D Printing. Now, a lot of you are probably going, okay, 3D printing's been around for 25 years. We've already imagined all the possibilities. Over the next 15 minutes or so, I will contend that we're at a tipping point. 3D printing, especially HP's 3D printing, is advancing to the point where we're going to start looking at new forms of manufacturing. And combined with other megatrends, which I'll talk about briefly, we're on the cusp, or actually entering into another industrial revolution, in particular the fourth industrial revolution. So let's talk a little bit about that. If you go back maybe 250 years ago, if you needed something built, you went into your village, right? If you needed a horseshoe, there was a dude, and he basically pounded it out. Might have taken him all day to make a horseshoe, all week to make a whole set. If you needed, some cloth, you basically went to your village and you found somebody else to make the cloth using the local stuff. Well, in the 1780s or so, with the rise of steam power and mechanical power, in particular, it rose in Manchester, England, with the textile, printing. Basically, that was the first industrial revolution, and it was responsible for Britain becoming a world power at that particular point, because they were the ones that basically got into that industrial revolution first. The next one occurred in the United States, mass production, really with the advent of electricity, and basically it allowed the United States to become industrial power at that time. The third one, more recently, most of our lifetimes, started to look at, IT, the ability to track parts all over the world, container shipping, the ability to ship, bulk materials to China, take advantage of low-cost labor, and then ship it back, and then track all that, and further levels of automation has allowed China to rise to power. Now we're basically entering a fourth industrial revolution with digital manufacturing, and there's a lot of different things that are basically coming to bear to basically enable that, including 3D printing. So let's talk about those. First and foremost is automation. There's been some previous speakers talking about that. The best example I have of that is, HP makes a smartwatch. And so we had a chance to look at some factories making smartwatches. And I looked at 2 that basically built the same number, maybe 1 million a year or so. One was in China, had a factory, 10,000 people putting these watches together. Another one in Japan had 3 people putting these together. It was all fully automated. And that's the kind of level of automation that's systematically improving. Artificial intelligence kind of plays into that as well. And under automation, I'll put autonomous vehicles as well, and we all know about that. Under machine learning, the best example I think of that is probably those, I travel a lot, and so I use Google Translator. And about 3 months ago, I noticed Google Translator got a whole lot better. Well, they put an artificial intelligence engine in there that actually went out and actually created its own language for basically going through and basically figuring out what's the best way to take one phrase from another. And so we're seeing a lot of big data, artificial intelligence come together. Another one, and some of the previous speakers have talked about this as well, Amazon, really the online marketplace. You can go there and basically you can find anything you want. It says Amazon, but there's hundreds, thousands, tens of thousands of other people putting their equipment on there. And it's not just the fact that you can go and find it, but it's the supply chain, it's the IT, how do they get those parts to you and so forth. And so that is a mega trend that's occurring. Another one is the Internet of Things. We have Intel here in town, so people are very familiar with, improving, processor speed, improving memory. But, one of the reasons why drones, have risen to prominence is I worked at Boeing Helicopters and actually worked on UAVs, where it took man-hours, to basically put together something that you can now put together on a Kickstarter and sell for $1,000. It's because of the Internet of Things. You can now get integrated sensors, accelerometers, gyros, and what have you, on a little Arduino board for a few bucks, right? And it's just systematically bringing more and more performance and sensors along that same Internet of Things. Of course, current politics, building walls, tax, unfavorable tax, trade wars is actually probably going to accelerate this as well as you start to look to how do I basically start to do more localized manufacturing. And then 3D printing, I'm going to talk a lot more about that. So how might that show up? I recently got to remodel our kitchen, and I was told that we needed a new toaster because the old toaster didn't match the remodeled kitchen. So I went to the store. And basically, you go to the store, and there's 6, maybe a dozen toasters. They're all produced, in China by all the people that we know, and there's a very limited set. So I did the best job I could. I picked the one home and brought it back, to be in the new remodeled kitchen. In the future, first, because of artificial intelligence and big data, the system's already going to know that you remodeled your house. The system's already going to know what colors you've remodeled your house. The system's going to know what your preferences are, or what your spouse's preferences are. And you're going to start seeing ads. And these ads are going to be from companies all over the world that basically start to show up. And they're going to start trying to figure out how to customize that toaster for you and attract you basically to that. Eventually, you're going to buy that, and you're going to select that company, wherever it is in the world, through this big supply chain in IT, to save money, they're going to build that on 3D printers that are fully automated, probably in your town or just up the street. So you'll see this effect around global access, but very local access as well. That means if you have a company, a design company, you want to specialize in toasters, you can, through the Amazon-like workplace, you can sell it worldwide, and then there'll be systems to basically have that built and have it be built really low cost. So mass customization, distributed manufacturing, disruption of supply chain. There will be no inventory. There will be no long tail. Stuff will be built when you need it, where you need it. Flexible capital. That assembly line, that 3D printer, and the automation that goes with that will build the toaster, it'll build your espresso machine, it'll build everything else that you have in your house as well. I already mentioned the sort of global access at a local level on both ends, both if you're a company selling it worldwide, but also if you're a manufacturer building something that was maybe designed somewhere else. Humans will be increasingly replaced by autonomous machines, right? The best example of this is trucks, right? Within 5 years, there'll be no more truck drivers, right? It'll all be autonomous. You'll probably wipe out 4 million jobs, overnight. So that level of autonomy, right? And so, I don't want to get political here, but if you look at the second revolution, the second industrial revolution, the US was primarily an agrarian society. 50% of people worked in agriculture. The government recognized that and basically created the high school program, started to retrain folks that they could be ready for this new industrial world. The countries that figure that out will win in this fourth industrial revolution. Okay, now let's talk a little bit about 3D printing. We're at a tipping point. HP, down in Corvallis, but also in Vancouver, Washington. It's our HP's largest site. It's a couple million square feet. I've got a few HP folks here to shout out to those folks. We've stayed vertically integrated. We make the print heads, print bars, inks for printers that cost $100 and printers, and we actually build the printers there that sell for $10 million as well. So it's kind of the mothership of inkjet technology. Well, it's becoming the mothership of 3D technology as well. And recently we've had some breakthroughs. Our printer will be 10 times faster than anything else that's out there. We'll build high quality parts. These are not the parts you're going to build on your $500 Kickstarter machine. I guarantee you do not want those holding your airplane or your car together, but these will be the same as injection molding from a material part standpoint. Lower cost than anything that's out there, about half. And the other thing we're going to do is we're going to take an open materials platform. Even though we're a great company, a lot of material scientists and so forth, we recognize that if we're going to figure out how to change the world and get 3D into manufacturing, we need a different way to do it. So we're creating an open platform. The analogy is very similar to Apple. They basically created an ecosystem. They have a software development kit. Developers can go out there, develop it. It gets certified in the Apple ecosystem. And now there's millions of applications. And people make billions of dollars on that. So our approach is exactly the same. We will have a materials development kit, an MDK. We recently had a press announcement announcing that open lab down in Corvallis to do exactly that, where we will allow material companies or whoever else to basically develop materials for other customers and then certify it into our system. And certify to make sure it's safe, that it has the right levels of quality and reliability. So that's going to be part of our tipping point that basically pushes the world into this next industrial revolution. So these are some of our partners. All these partners are folks who recognize this industrial revolution is coming, and they are looking for transformational opportunities relative to their manufacturing, their supply chain, how they do design, and so forth. And there's a few companies, as you see, that are located here in the Northwest. So one thing that people don't realize today, with our system, with our current levels of productivity, if you take a part, and this is actually a part out of the printer itself, about 1.5 inches, in diameter, ½ inch thick. If you take this part, if you're going to injection mold it, you have to go out and you buy a $100,000 injection molding machine and the molds or what have you. If you build one part, you have $100,000 of machine capital and a little bit of plastic, right? If you build millions of parts, eventually you just get down to the cost of plastic. Well, with 3D printing, the cost is pretty much flat. So that's that orange line across that spot there. With our current level of productivity and this particular material and the current cost of that, it's cheaper to build 55,000 of these today to build this particular part. So if you're doing short-run production, you would never use analog. And so, already this is economically feasible for short-run production. Because of our open materials platform, as we move ahead on materials breadth and looking at cost, we have a roadmap to systematically over the next couple of years take this part and actually get to the point where it's break even. So this is part of the revolution, is that you will not use manufacturing methods that have been used before, like where you basically have them done overseas. You'll basically have printers that are co-located with your assembly line that print what you need, where you need, when you need it, and only how much you need it. So, I'd like to talk about this. The printer prints itself. The printer, we could probably print most of it, but when we basically took a look at the printer, we decided, hey, because of the previous economics, let's go and take a look at where it made sense, where it actually makes sense for HP to actually use it. And so when we basically did this analysis, we found that about half of the custom parts was actually cheaper to print them than to use analog methods. Now, to be fair, we have not yet started printing. We just released this product 4 months ago, and most of our hardware is focused on first sales, but we're going to systematically start replacing the parts in there with our own. And that doesn't get into the fact that this part here previously was like 12 parts and 8 screws and 2 welds, right? So as you start to redesign things, you can take about 80% of the cost out of that manufacturing assembly by just 3D printing that entire thing. Of course, if you look at that same roadmap I showed, where we get to 1 million parts for that little gear, we get up to 75% of the parts are basically economical. And you can see the parts start to get bigger and bigger. And so we feel that this value proposition is key to being a part of this tipping point into this next industrial revolution along with these other megatrends. But wait, there's more. Because we're using our thermal inkjet technology, we have the ability to actually jet different materials down. And this particular cartoon here, we call it a voxel. So if you think of, when you print an image, you have a pixel, right? Well, a voxel is sort of a three-dimensional, a volumetric pixel. And we start with a powder-based system. We basically melt that powder to, think of it injection molding layer by layer. But we have the ability with our inkjet technology to jet other things into that voxel, into that powder location. And that's kind of shown here. We might start with a powder in white, and then we have these little orange things that could be something else. And so you're saying, well, what could those things be? Well, first and foremost, you might do color, right? And so, let's see if I can pull these out here. So you can imagine jetting, pigments and so forth in there, right? To basically create different colors. And now you don't just have black, but you can basically start to make functional parts in, different colors by basically jetting that in there. Okay, that's kind of interesting. But another thing we can do is you can jet down reactive agents. You can actually change how that polymer basically comes together. So you can make like a screwdriver handle where the inside of the screwdriver is very rigid, right? Because it has to hold onto the steel part, but the outside becomes very soft so that your hand can basically grip it. So basically we can change the elasticity on any of those different locations. We can change the texture, right? So maybe we jet some silica or something like that, so basically it has better wear parameters. One thing we've done recently is we've actually jetted metal nanoparticles into it and actually built a printed circuit board through it. And we actually built a strain gauge, and I think I have that part too. So we have a chain link. We basically printed a strain gauge through there for all the electrical engineers in a Wheatstone bridge pattern. So we basically put that in a load. Basically, it becomes a nice load cell. It's also a temperature sensor. It can actually be a heater. And so we can already embed simple circuits. So you can imagine this part in the future having embedded electronics on it. So basically, it's talking to the printer. Or probably a better application would be trucks, right? Those autonomous trucks with no drivers, they're factories on wheels, right? Every part would be able to talk to the truck and talk about its health. I'm here, I'm healthy, and what have you. And so as you think about the industrial Internet of Things, very low cost, we can integrate that in there. And so now in the future, in the near future, we'll be able to build a part, we'll be able to change the material properties across that entire part. Color, elasticity, conductivity, tribological things. And if you think about it, this is made up of, I don't know, 4 or 5 trillion voxels. I can engineer things that are completely impossible to basically build, in the past. And so that's part of our long-term vision, which is not only will it be economical and start to compete, but we'll be able to integrate things that the world's never seen in this next industrial revolution. So this last video, and then we'll call it quits.
Designers and engineers, captains of industry, and leaders of thought. Anyone whose ambitions have ever exceeded what was possible. This is your moment. Your rewrite history, the world is not flat moment. Every facet of how you design and manufacture is about to be reinvented, and it all starts here. With the smallest of building blocks, the mighty, you and it are about to change the world by advancing radical prototyping, accelerating manufacturing, and taking precision and strength to unheard of heights. From today forward, the 3D printer is a factory for thought, where the things we make will make us smarter, better, more human. What a future we'll create with new materials and embedded intelligence. Together, we'll bring extraordinary to the everyday and reality to dreams light years away. Welcome to the age of digital production, on demand, a world without waste, without inventory, without warehouses. Meet the first HP Jet Fusion 3D printers, the digital furnaces of the next industrial revolution. Join us as we engineer the never-before, voxel by voxel. HP Multi-Jet Fusion. Keep reinventing.
Great, so that concludes my prepared materials. I think Mike's going to come out and we'll take a few questions. Maybe the final point while he's coming out is that this is all being done in the Willamette Valley, right, between Corvallis and Vancouver. So a lot of really cool technology and opportunity to position the state actually in the core of that next industrial revolution. Mike?
Hey, Tim. Thanks very much. So I'm Mike Rogoway. I'm the technology reporter at the Oregonian, and we'll take some questions for Tim. I've got a couple of my own first. We'll kick off. Tim, in your presentation about the new industrial revolution, you talked about artificial intelligence, you talked about the Internet of Things. These are things we associate with Silicon Valley, the tech capitals of the world. 3D printing for HP is coming out of Corvallis, small town in the Willamette Valley in Vancouver. What's the reason for that? What's the legacy that HP has in those areas, and how is the company using that technology?
Yeah, great question. I've spent the last 24 years in Corvallis working for HP, and it's really, I call it the technology mothership for HP. The PC, the first laptop was invented there. The HP calculator was basically invented there. We have probably a huge manufacturing facility with stayed vertically integrated. We've never moved our printing technology outside HP's walls. And as I mentioned, we make everything from 100 to $10 million type printers. That's where we have the infrastructure, and probably more importantly, the brain power. The material scientists are able to come into this and actually start to develop the materials and the various agents that I talked about, to engineer at the voxel level.
It's fascinating to me that the technology that you created for the inkjet printer, for two-dimensional printing, can be applied to 3D printing, that some of the same principles work.
Absolutely.
That's really interesting. When we talk about this coming industrial revolution and the advent of 3D printing, you talked about products already that you're ready to start printing, and HP products that you start selling commercially. What do you think the tipping point for 3D printing will be? What's the killer app, do you think, that we'll start to see this become something that people feel in their everyday lives?
I think it'll start to show up very, very soon, like now, and for short-run production. Manufacturing was almost completely driven by economics, right? It was cheaper to ship stuff to China, have it assembled, and bring it back, so people did it that way. At the point, especially for short-run production, where it's actually cheaper to print those parts, or rather than print or have 6 different parts, print all the parts together. I think as manufacturers, and you can see some of the forward-thinking companies start to realize that, it'll be all about the economics, and they will basically start to switch over. Being able to engineer at the voxel level will come next once people or manufacturers see the power in basically saving money, right? And by doing it with the local manufacturing.
What industries do you think we'll see that first? Is that automotive? Is that electronics? What do you think
A lot of the verticals, the different markets are driven by their life cycle, right? So if you look at aviation, even though they probably have the most to gain because you can lightweight different parts and so forth, very long regulatory cycle. Automotives tend to be about a 4 to 5 year cycle. Consumer tends to be more like 18 months, right? And so I think we'll start to see it there first. But there's also medical and tooling and I would say space and defense as well.
Do you think there's a timeline for when people start to use this themselves in their everyday lives, outside of manufacturing, but something that they would use?
Well, to be clear about HB's technology, it is designed for industrial manufacturing,
yes.
Right? The Tech Fest guys here said, hey, can we bring a machine in? Well, it's about the size of the stage, right? And so it's, unless you have a couple $100,000 to spend, you're not going to see ours in the consumer market. There's a lot of very good, I would say desktop printers that are great for form and fit and prototyping, and a lot of people who have that interest are using them today. The power we have here is making something that you would be safe enough to be in the airplane or your car.
Excellent. Do we have some questions out here? Anyone have ideas?
How big is a voxel was the question. And so it's leveraged from our 2D technology, and it turns out the threshold of what the human eye can see is about 22 microns, and a human hair is about 50 microns, so about half the diameter of a human hair. Because we're leveraging that technology, that little cartoon, that voxel I showed, is about 22 microns by 22 microns by the layer thickness, which can be highly variable, up to 100 down to, say, 50 or so.
Do we have other questions?
How do you, with a lot of mission critical parts, like if you were talking about automotive, how do you manage quality and liability associated with that?
It's a great question. So how do we manage quality and reliability? And probably the same way you do it with injection molding today. As we build a manufacturing machine, we'll have process control, process monitoring. We'll basically have parts that we build and break to make sure they're adhering to that. Which is exactly what you do if you're injection molding that today. If you're doing 1 million parts, you would test every so often and basically build a rigorous quality system around that, which is what most of the regulatory requires anyway in order to basically do that. So it's probably very similar to what is currently done for manufacturing parts. Good question.
Do we have others? Yeah, right here in the center. What materials can or can't be used so far?
Our system works today on thermoplastics, in particular semi-crystalline thermoplastics. We introduced with a polyamide, a nylon. We'll have a number of variations of that. Over time, we'll have other things like POM, PBT, polyethylene, polypropylene, things that you would normally see systematically, especially with our open materials platform. We have a number of material companies like BASF working down in Corvallis developing these materials, so systematically we'll have more over time.
And Tim, I don't know if people said this during your introduction, but I believe you mentioned the nylon materials. That's what you use to print the awards for the startups for today.
Yeah, so those of you going to the pitch downstairs, but the folks who win that, luckily our team was able to use our printer to print some pretty cool looking awards, so please take a look at that if you're going down there.
Tim, what are the biggest technical challenges? What's at the top of your list that say, hey, if we can solve this, we've opened another door for something?
Yeah, so I'm an engineer by background, and so to really answer that question, we have to kind of nerd out a little bit. It turns out when you basically are melting plastic, like you would with injection molding, the way to think of this is it's a layer process versus a point process. When we basically put heat in to melt that, if you have a great big part, it's going to heat up differently than a small part. So our challenge is how do we manage the thermals to basically make it so we can make reliable parts that are the same across the entire build volume every single time, which goes back to this gentleman's question, how do we ensure quality across that? Luckily, again, leveraging our 2D land, where we have a lot of modelers and a lot of PhDs in material science, we're able to leverage that to basically develop the algorithms to do that.
Good. Have other questions? Yeah. First, we'll do the table, and then we'll move up to the row. Yeah, right there.
I'm interested in how the newspaper industry and the journalism, you being on the stage there from the Oregonian, how this is affecting journalism.
Well, I wouldn't say 3D printing is affecting us necessarily, but certainly commercial printing has. The days of the giant press and things are behind us. You can print much more efficiently now. I mean, they're not totally behind us. Huge volumes still done that way. But in smaller volumes, you can print using newer technologies without the huge printing press that we used to have. And in fact, we sold our press across from Providence Park.
What do you mean by organics? Because technically these are organic polymers, right? Like bio-type materials?
Yeah, the question is printing with organic bio-type materials.
Yeah, and so it turns out our inkjet technology actually works fairly well. We're not doing any active research, but we're sponsoring some at a number of universities, and you can use it to actually jet cells and what have you for, I think one of the first ones that looks promising is to replace knees in old men like myself, so the meniscus and cartilage and so forth, but there's a lot of other work. The issue I think with that is it's very long lead time, right? It's exploratory research, but if we think there's a long regulatory cycle in aviation, putting something in the human body is a little bit longer, but it's coming eventually.
I think we have time for one more question. Yeah, at this table over here.
It only took 3 people in Japan. What are the type of skills or education or knowledge they need compared to today's workers?
It's a great question. When you start to move to a 3D printer, printing all the parts there, and automation, putting your stuff together in very low cost sensors and Arduinos or what have you, basically what you need is probably a lot more 2-year technicians, folks who have a background in mechatronics, both on the software side, the firmware side, and the ability to repair tools. And so if we think about what do we need to do differently, kind of like when we basically created the high school system back in the early 1900s, it's probably a lot around creating proficient technicians, which is probably a 2 or 3 year degree. My take.
In the interim, are you taking people from existing fields and adapting them to this?
For our work, absolutely. Leveraging the great workforce that we have, both engineers and technicians. I think this question here is more around what happens when everybody's producing all their parts with these types of automation and 3D printing. You need a workforce that has basically been trained to basically operate in that field.
Got it. I think we do have time for one more. If somebody, yes, at this table back here.
So for your traditional printers, you have printing speed like 33 pages a minute, things like that. How do you measure printing speed of a 3D printer? For example, you have that nice part up there you said that you printed. How many of those can you print in what amount of time?
Yeah, it's a great question. So how fast? And speed's probably not the best one here. It's really around productivity. We have a powder bed, I think it's 12 inches by 14 by 16, that we basically build parts in. So it's how many parts do you build in that total, over a period of time. You saw it in the video, that was real time, right? So the speed is basically, how fast can I spread a layer of powder? How fast can I then jet a fusing agent down and then pass a heat source where the fusing agent absorbs the energy and actually melts? And that video is real time. It's literally spread, print, fuse. So about 8 seconds per layer, that's where we get, order of magnitude or more speed improvement over any 3D printing technology that's out there. Using the page-wide technology developed where? Corvallis in Vancouver.
Excellent. Tim, thank you very much.